Okay, so let me begin. Let's start with today. So we are going to cover this is AEC module 1.3 revision. Okay, and we are going to start with BJT as an amplifier. Okay, I whatever I'm writing over here, is it visible enough to you? Can someone confirm?
Yes, sir.
Okay, so let me give you a brief about BJT as an amplifier. Let me see if, yeah, admit. Okay, so in BJT amplifier, basically we have three types. We have common emitter amplifier, and then we have common base amplifier, and then we have common collector amplifier. Okay, so what are we supposed to do in this module is, so what we do is, for all of them we'll analyze the amplifier, we'll analyze the amplifier circuits. Okay, and for all of them we'll calculate the following: voltage gain, then we'll calculate input impedance Z in and output impedance Z out for all of them. Okay, voltage gain Z in, Z out. Again over here, voltage gain Z in, Z out. Now this is the derivation part. So there will be derivations for expressions. So you have to derive the expressions for these things. Okay, derive the expression of small signal voltage gain AV, Z in or Z out. So it can be asked for any of the amplifier: common emitter, common base and common collector. On the second part is you will have numerical. So in numerical, they will give you the amplifier configuration, and they will ask you to calculate voltage gain Z in, Z out. But you cannot calculate it directly. So you need to calculate, let's say IDQ, then you can calculate GM, RO. So we need to calculate these first and then this first. Okay. Now all of this is possible with the help of small signal model. So we need to know the small signal hybrid pi model. And this small signal hybrid pi model, as we know, I think it's contain R pi also, right? Yeah. It is made up of three elements, which is uh, GM, then R pi is there, then then RO is also there. So these things will comprise the small signal hybrid pi model. Okay, so far so clear. What we need to do, we need to analyze amplifier, that means derive the expression for small signal voltage gain AV, input impedance Z in, output impedance Z out. Okay, and in the numerical form they can ask you in the numerical also, we need to find the IDQ nahi ICQ, sorry, ICQ, GM, RO, R pi. Then we need to find AV, Z in and Z out. So we will do this for, we will do the derivation for one and solve the numerical for one, and other two will study in comparative study. Okay, in comparison we'll study because we have limited time. All right. Okay, understood what is required.
सर
Yeah.
रिकॉर्डिंग करोगे क्या?
Yes, I am recording it. I don't know whether it will record properly, but I've turned on the recording.
अच्छा किया है क्या सर? ठीक है.
Okay, okay. Yeah.
ओके, थैंक यू सर.
You have any doubt in this, whatever I'm explaining till now?
नहीं सर, नहीं सर, ठीक है, समझ रहे हैं.
Okay, fine. So I'll proceed further slowly. Now we'll understand what is this small signal hybrid pi model. I'll revise it for I think 2-3 minutes first. So what is the existence of this small signal hybrid pi model. Even though I've explained it last time, still I will switch to explain it. So, what is the symbol of a BJT? NPN BJT, like this. This is my collector, this is my base terminal, and this is my emitter terminal. Alright. Now, in drawing this model, we will first draw the base terminal, then the collector terminal, and emitter terminal will come over here. Okay. Now, what does this model says is, it says that between base and emitter, there is small signal resistance. So that resistance is represented by R pi. Okay, so this is my base. All right, and between collector and emitter there is a current flowing, right? IC, and that current IC is given by Gm into V pi. Now what is V pi over here? This voltage is V pi. All right, so Gm into V pi, and there is one more component over here which is the output resistance of the BJT, Ro. Okay, fine. So what are the formulas of, and why there is nothing connected between base and collector? You remember, in the forward active, this model, this hybrid pi model is valid only for, let me write over here, this model is valid for BJT to be in active region. Okay, so we assume that BJT is in active region for this small signal model analysis. Now, what is the base collector junction when the BJT is in active region? What is the state of base collector junction? It's reverse bias, right? And what is the state of base emitter junction? It's forward bias. So this is the answer why base and collector is open circuit, because it is reverse bias. All right. Now what all these quantities represent? First of all, write down the formulas which will fetch you marks. So write down the formula for R pi. R pi is given by beta upon Gm. Its unit is in ohms. Okay. Then next is Gm. Its value is ICQ upon Vt. Vt is the terminal voltage, and its value, its unit is milliampere per volt. Okay, the answer will you will get it in ampere per volt, but convert it into milliampere per volt. It's easy for further analysis. Okay, and another formula is Ro. So this is number one, two. Another formula is Ro. Write it down. It's Va upon ICQ. And what is Va? Anyone knows? Va is called as early voltage. Early voltage. And what is Vt called as? It's a thermal voltage. Its value is 26 millivolt at room temperature. Room temperature is 27 degrees Celsius. Okay. So in a numerical, they'll give you the value of, okay, sorry. So in a numerical, they will give you the value of given data will be always beta. Beta will also be given and Va will be given. If Va is not given, understand that Ro is infinite. Okay, and they will not give you the value of VB. So VB on or VB. So assume it to be zero point 0.7. So you need to 0.7 volt. So assume this. They will definitely not give you the value of VB. It is assumed to be zero point 0.7. Okay. So for a BJT, any numerical BJT amplifier or BJT DC analysis, they'll give you the value of beta and Va. Okay, and from that you have to do the DC analysis and find out the value of R pi, Gm, and Ro, and draw the hybrid pi model. I mean, we will do now next what to do further. Okay. Any doubt in considering this in hybrid pi model? Any doubt you have? Hello.
No, sir.
Okay. I'll briefly tell you that what is this hybrid pi model. It's an approximation. So I am drawing my input characteristics of a BJT, how does it look like? It looks like a exponential curve, right? Let me draw a proper exponential like this, or even more proper. Yeah, like this. Now, in this exponential curve, if you see carefully, small segment of this exponential curve is linear. See this part, it's linear, right? So what we do is we consider this linear segment, this consider this straight line, and in this straight line we mark here VBQ and we mark here IBQ, or accordingly we calculate ICQ also. ICQ will be beta times IBQ, so we can calculate this also. Okay, so under this small segment will vary our AC signal. Okay, so that means if my VBQ is like this, let's say my VBQ signal looks like this, and this is versus time, huh? This is your small AC signal VBQ. So this will be the DC value of it. Let's say it's 700 millivolt. So what will be my small signal AC signal? AC signal will look like this. So this is my AC and this is DC. All right. So this is what this means. And this AC signal has to be very, very small in millivolt, few millivolts. Okay. And why it has to be small? Because it has to follow this range, right? It has to be followed this range. So it should be this small. Because if it violates this range, then it will go into exponential curve, then it will become non-linear. So basically what we are doing is we are linearizing the non-linear BJT. See, this exponential curve is non-linear and we are only taking a straight line. Now, whatever the straight line limits are, that will be the limit of the input signal. Are you understanding? So similarly, your IBQ. So IBQ signal might look like this. Okay, this might be the value of, let's say IBQ. That value, let's say it's 40 microamperes. And what you get AC signal is very small. Okay, AC signal might be, 1 microampere long. So this is how it looks like, and this is IB. The small IB, small VB represents AC quantities. Are you understanding? So when we do hybrid, when we draw that hybrid pi model, R pi represents the input resistance of the device. Okay, R pi represents the input resistance of the device. This is R pi is input resistance of BJT. Okay, and it represents only the changes. Now since you were there, those who were there last time knows that we have done this. So R pi represents what? Changes in VB upon change in IB. It represents only changes in VB and changes in IB. Okay, so these are small changes in VB upon small changes in IB. All right, and there was one more relation. V pi we used to write it as VBE, small VBE. Okay, and the changes in VB actually. Okay, changes in VB we write it as delta VB. Let me rewrite it. V pi we used to write small changes in VBE. So these small changes in VBE, I mean, how do we relate GM? GM was change in IC, small changes in IC upon small changes in VBE. Let me write VBE properly. Yeah, delta VBE. So what was small changes in IC given by GM times VBE? So this changes in VB we used to write it as GM pi. So this delta IC is represented by GM pi current source. Okay, voltage dependent current source. This GM pi. All right, are you understanding? And what was RO actually? Now, if you see the output characteristics of a BJT, common emitter BJT, it looks like this. It used to look like this, right? Straight line, straight line. But in reality, the characteristics is like this. Let me draw with different color. SA. It increases actually. It doesn't stays constant. It increases, and this is due to early effect. This is IC versus VCE graph. VCE, sorry. Okay. So there is a slope to this curve, right? There is a slope to this. This is the slope, and this is determining my RO. So RO was actually given by delta VCE upon delta IC, to small changes in collector to emitter voltage divided by small changes in IC. Okay, so this was RO. So that means every quantity in this small signal hybrid pi model represents small changes in its values. Is it fine? Now you have understood the theory behind the hybrid pi model. Can we proceed forward, or you have a doubt? Hello, anyone have any doubt before? No, because now we are going to amplifier part. Okay, all right, fine. So we'll now move on to the amplifier part. So this is what the small signal hybrid pi model means. It represents small deviation in various quantities, just like VB, IB, VCE, right? Small changes in quantities. It represents only small signal time varying quantities. All are time varying quantities. Okay. So what are the condition for the amplifier? The condition of the amplifier should be that input signal should be small. Now why input signal should be small? Because of this straight line approximation. We are doing straight line approximation over here. So this is straight line approximation. So what are we actually doing by drawing this model? This model is linearizing the non-linear BJT. So if as long as the input is small enough to be in this linear segment as a straight line, till then this model is valid. Okay, because above that it becomes non-linear and this model will not be valid. That's why in a practical lab also, whenever you have applied input to the amplifier, it is small millivolts only. Yeah, I think you have applied around 30, 40, 50 millivolts. So if you apply it a higher value than that, you can try it out next time whenever you go in your lab. If you apply a higher value, then the output will be distorted. Okay, because for an amplifier, now let's start building an amplifier. So for a good faithful amplifier, you apply input, right? You want amplification. Okay, so you apply AC input signal, very small AC input signal, and you expect that output will be a large variation of that. All right, so this is V out of T and V in of T. So this is one condition to be amplifier, that AV should be high, gain should be high. But this amplifier should be linear also. What do you mean by linear amplifier? If input is sinusoidal, output also is a sinusoidal. Okay, output should not be like this. This is not required. This is non-linear. This is linear. Are you following what I'm saying? This is also so. If the sinusoidal for the sinusoidal input, small sinusoidal input, we get a large variation in the output, which is again sinusoidal. Then it is a linear amplifier. If it is anything other than that, if it is distorted, then it's non-linear. Okay, so these are the requirements. Also, its input impedance should be taken care of, and output impedance. Input impedance will decide how you connect, what you connect at the input. So input impedance has to be very high for voltage amplifier. Now we are talking about voltage amplifier, and for output impedance should be low. Okay, generally speaking, that is good for voltage amplifier. So input impedance should be high and output impedance should be low for amplifier part, and gain should be high, and also it should be a linear amplifier. So these are the conditions for amplifier part. Is that fine? Also, there is one more important condition. What is the condition? Amplifier should be applied DC voltage, so that it generates, for a BJT voltage amplifier, you should apply DC voltage to the amplifier also, to the circuit actually. All right, everyone ready? So let's begin with the first configuration, that is common emitter amplifier. So please draw the circuit. Common emitter will do in detail, and then others will study relatively. Common emitter amplifier. Now let's draw the circuit of it. So first of all, draw the this voltage divider biasing circuit. So how does the voltage divider biasing circuit is like this? Okay, this R1 and R2 over here are the potential divider. Okay, so let's say you apply 10 volt over here. If R1 and R2 is same, then it will give you 5 volt over here, right? So that's the meaning of voltage divider. All right, and the same voltage will be given over here, and this is your VCC, this is RC, this is RE. So this is my voltage divider circuit, which we have discussed last time already, which must be discussed in your class also. Okay, mark the terminals as base, collector, and emitter. Okay, now tell me, um, for an amplifier, right now, this will have some DC current, right? This will have some current IC, and it will have DC voltage at the collector, emitter, and base terminal. Yes or no? So at the base terminal, you will have a DC voltage of VB, base voltage. At the collector also, you'll have DC voltage, and emitter also you have this DC voltage. Now you apply your AC signal. Now, if I directly apply the AC signal, the AC and DC will interfere with each other, and that will lead to the wrong result, or the saturated value, or not the desired value. We can say that. So, to isolate the AC and DC, we apply capacitors in between them. So, this is the capacitor number one. This is the output capacitor, output coupling capacitor, and there is one more capacitor, that is bypass capacitor, going to the ground. Okay, this is CC1, input coupling capacitor, this is CC2, output coupling capacitor, right? And this is CE, which is the bypass capacitor, and here you apply the input like this. Okay, this is V in, and at the output you can connect a load resistor. So this is my load RL, and that's my output V out. I can mark that as V out. So please draw the circuit. Okay, so this is plus minus V out. So which are the AC quantities over here? Let me mark. This is DC, VCC is DC, this is AC, and this should be AC. Remember, capacitor will block DC voltage. It will allow AC to pass through. Alright. So how do you identify whether this configuration is common emitter? In common emitter configuration, if you see carefully, input is applied to the base. So input is applied to the base, and output is taken from the collector. So output is taken from the collector. So whenever in an amplifier, input is applied to the base terminal and output is taken from the collector, that amplifier is called as a common emitter amplifier. So have you all drawn it? Any doubt in this? The circuit diagram of common emitter amplifier?
No, sir.
Alright. Now, in this amplifier, we can break it down into sections. So this part over here, to the left hand side of this gray line here, this is called as source. Okay, and over here to the right hand side of this RL, this is my load, and in between we have the amplifier. Okay, so this is my amplifier part, this is my source, this is my amplifier part, and that is my load. That is why RL is called as a load resistance.
Sir,
Yes.
how do we decide these ये lines कैसे draw करना है exactly? How do we decide this?
Which lines?
वही जो अभी source amplifier load के लिए you're separating them ना? So वही
Yeah.
पूछ रहा हूँ. How do we exactly separate this?
So in case of source, we can have RSig also here, RSig also present. So source is the source voltage along with the internal resistance. So that becomes my source. Are you getting it? So that itself is my source. Whenever we start to draw the capacitor, from there the amplifier starts. And at the output also we can have RL. That's it. So after the at the output side after the capacitor, and an input side before the capacitor, that is my source. Got it? Yeah. No, it is
So
just
I
an
think
inform.
आपका lag हो रहा है voice.
Voice is
Yes,
lagging.
sir, it was breaking.
Now it's fine. Hello. Is my voice okay now? Hello.
तो वो स्टार्टिंग से ही मतलब स्टार्टिंग से ही आपने वो बनाया था सोर्स के वापस सिग्नल वाला रेजिस्टेंस स्टार्टिंग से ही बता दो वापस.
Okay, okay. This while I was
हाँ
drawing the circuit till then I was okay.
हाँ हाँ टिल सर्किट बना दिया तब तक ठीक था फिर
Okay,
उसके
okay.
बाद
Okay, okay.
सोर्स से बताने का है.
Got it,
हाँ.
got it. So, source is basically my AC input. Okay. So this AC input can have my internal resistance. So that is my RSIC value. Okay. So just you remember, anything before the capacitor at the input side is my source, and anything after the capacitor at the output side is my load. Okay. So this is my load and this is my source. Now, did you get it? It's just a
यस
representation,
सर.
nothing more than that. It's just a representation to distinguish between source and load. That's it. All right.
ओके. हाँ
Okay.
सर.
And I am deliberately not including RSIG over here because if they ask you this derivation in the exam, keep it as simple as possible. We will make it complicated in numerical, that is fine. But while they ask you derivation, keep it as simple as possible. Okay. Fine.
यस सर.
Understood, everyone? Now, for any amplifier, we have DC analysis and AC analysis, right? So, what does the DC analysis say? Let me show you. I had two analysis, DC analysis. So, what do you mean by DC analysis, or what do we do in the DC analysis? In DC analysis, we consider all connected capacitors as as open circuit. And why we do that? For DC frequency is 0, reactance offered by the capacitance will be 1 upon 2 pi f, right? C, which will be infinite. So if the reactance offered by the capacitance is infinite, all the capacitors will behave as a open circuit. Now, how does circuit diagram will look like? It will look like your normal base emitter. Your voltage divider bias this way. So this is your DC analysis, which you have already completed. So you need not draw this. I'm just informing you for your information. This is R1, R2, this is RC, and this is RE. So this is a normal DC analysis. From this DC analysis, what do we get? We'll plot the, we'll plot the DC load line, let's say, to interpret it better. So DC load line, and I've taught you last time how to plot a DC load line. We identified a Q point. So that will be VCEQ and ICQ, and we fix it, and we don't want this Q point to shift further. So if the Q point is shifting towards the upper side, that means it is going in saturation, and if the Q point is shifting to bottom side, that means the transistor is going towards the cutoff region. Okay, so you should operate it in the active region, forward active region always. This biasing will make so that transistor operates in the active region. Okay, so this is what the result is. This is what your DC analysis will give it to you. Okay, your Q point, stable Q point. And normally we also say that this Q point should be in the center of the DC load line. This is my DC load line. DC load line. Okay, this is what we have discussed last time. So let's start with AC analysis. Any doubt over here? I hope the voice is okay now.
Yes, sir, it is
Yeah.
fine.
Are you all following whatever I am doing? Because I am only speaking.
हाँ
Yes?
सर.
Yes, sir.
Acha,
Fine.
okay. Now we'll come to business and we'll talk about AC analysis. Okay. So for the AC analysis, so you can write down from now after you have drawn the circuit. So for the AC analysis, we have the following assumption. We'll assume that all connected capacitors behave as short circuit. We'll assume, this is an assumption, okay? And along with it, we'll also assume that your DC supply, any independent source, DC supply also you short circuit it. Anyone can tell me why we short circuit DC supply? Because in a small signal AC analysis, there is no quantity which is fixed. It is all quantities are time varying. And DC is not a time varying quantity. That is why DC supply also short circuit. Did you get it?
Yes, sir.
Okay. Now we'll draw the circuit again. Okay. Replacing all the capacitors by a short circuit. Like this. Okay. All the resistors will be intact. Yeah, sorry for it. Resistors you draw it as it is. This is my ground. Okay. Now this AC, this will be short circuited. So I'm connecting it to ground. This will be short circuited, connecting it to ground. Then what about capacitor CC1? It will be short circuited over here like this. And here I'll apply input V in. Similarly, at the emitter terminal also there will be a short going to the ground. And here also there will be a short and there will be a RL connected. Okay. And this is my V out. So this circuit is called as AC equivalent circuit. Actually, in the exam, if you draw this, it's fine, but there are no marks for this circuit. You need to draw what I'm drawing next circuit. This is fine. This is to understand. It's very important. Did you understand how the circuit came now? All connected capacitors behave as short circuit, and DC power supply short circuit because it represent only small time varying quantities. Okay, everyone has reached here.
Yes, sir.
So this is my collector, this is my base terminal, and this is my emitter terminal. Now in the next step, what I will do is replace BJT by its hybrid pi model. You remember we have discussed hybrid pi model. We will be replacing the BJT with its hybrid pi model. Okay. So can we start now? So we'll be replacing
Yes, sir.
this transistor now. See this transistor we cannot proceed it further because it's non-linear. And what is small signal hybrid pi model? The linearized version of this non-linear BJT. So that we can analyze the circuit further. So let's do that. Let's draw the circuit. Let me draw it over here. Okay. Yeah. First I'll draw only the hybrid pi model. So what does the hybrid? How does the hybrid pi model look like? You draw the base terminal first. Then you take the collector terminal. This is my collector terminal. And then at the down you take the emitter terminal. Right? That's how you draw. What is connected between base and emitter again? R pi. Don't forget that. And what is the voltage across R pi? V pi. Okay. What is between collector and emitter? Gm into V pi. And there is small RO also connected. You can avoid doing connecting RO, but it's fine. I want to include RO. Okay. So this is my hybrid pi model. That yellow color portion which I have drawn is this. Okay. Fine. Now I'll go over here. Have you drawn this model? Okay. Now I'll go over here and I'll check what all things I will draw. Now from the base terminal, is my R1 R2 in parallel going to the ground? Yes, no? Correct? R1 and R2 are in
Yes, sir.
parallel
Yes.
going to the ground and we have V in connected. So over here, I'll go over here and draw in blue color. I'll have R1 and R2 in parallel to each other and they are going to ground. So I can write R1 parallel to R2 together. And I have V in connected at the base terminal also. So here it is. Alright. Now I'll go to the emitter terminal and check above. So in the emitter terminal, there is a short circuit going to the ground and there is a resistor RE. So what will happen now? RE register will become redundant because there is a short circuit. So emitter terminal will be directly going to the ground. Okay. So I'll connect the emitter terminal directly to the ground. Now next at the collector terminal, I have RC going to the ground and RL also going to the ground from the collector terminal to the ground terminal, and then I have a V out connected. So let's make that connection. I have over here RC going to the ground, and now I have RL going to the ground. RL, RC, and I have a V out connected at the output like this. So this circuit is called as small signal equivalent circuit. So let me write it. Small signal in the syllabus is written mid frequency, but it's fine. Small signal AC equivalent circuit. Okay, everyone has understood how to draw this. First, correctly drawing this, half of your job will be done. Everyone understood?
Yeah, sir.
Okay. Now we'll analyze this circuit and we'll derive the following expressions. We'll derive AV expression, we'll derive ZIN expression, and we'll derive Z out expression. All three of them. Okay. So can we start?
Yes, sir. Yeah, sir.
Okay. So first is I'll keep this circuit as it is and I'll do the derivation from here. Okay. First we'll start with small signal voltage gain derivation. Okay, expression for AV. So for this, and first tell me what is gain, voltage gain. It's basically output voltage divided by input voltage. That is my voltage gain. So I have to relate V out and V in together. So let's start. Okay, now tell me if this is V out and this is RL, what is the current flowing over here through RL like this? It is V out upon RL, right?
RL.
Yeah. So this current will be V out upon RC,
See.
and this current will be V out upon RO, correct? And this is also current source. So now what I will do is now I'll apply step number A, KCL at collector node. So what does the KCL at collector node give me? All the currents are there are four currents flowing out of the terminal, right? So I'll add them all together, right? Incoming currents is equal to outgoing currents, correct? So I'll write Gm into V pi plus V out upon RO plus V out upon RC plus V out upon RL is equal to 0. Correct? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now tell me what is V pi? What is V pi and V in relation? Are they same?
Yes, sir.
Yeah. So actually V in and V pi are in parallel. So they are same. So instead of GM V pi, we'll write GM V in. So I'll write GM V in is equal to, I'll take everything on that side, I'll write minus V out into 1 upon RO plus 1 upon RC plus 1 upon RL. Okay. And now from here it's easy to determine AV, right? So what will be AV now? So what is 1 upon RO plus 1 upon RC plus 1 upon RL? AV is V out upon V in, so that will be minus GM into RO parallel to RC parallel to RL. Got it? This is the
Yeah,
formula.
sir.
This is the formula. This is the formula for voltage gain. Does anyone know what does the negative sign indicate?
Input and output are out of phase by 180 degrees.
Perfect. So if they tell you, let me rewrite this formula over here. I mean, let me draw the input output waveform. So if I draw the input output waveform, if this is my V in and this is my, let's say, V out versus time, If my input waveform is like this, okay, my output waveform will be how? Out of phase signal. But yeah, like this. Correct? So this is my V out of t, and this is my V in of t. So if they ask you to draw the input output waveform, you have to draw it like this. Okay? Understood? The negative sign will indicate that uh, it's input and output are out of phase. That's correct. Okay? Are you understanding? Okay. In this formula, now this formula can generally be shortened down. It can be written as GM into RC. That's it. How, when can we write that? This is when RO is infinite and RL is not given. So RL is also infinite. Okay. So this can be simplified to just one thing, minus GMRC. Is this okay? Is this clear to you?
Yeah, sir.
Okay. Now, let me,
Sir,
yeah,
can you explain again what's the graph called? The V and V out graph?
this is input output characteristics. Input
Okay.
characteristics, nahi, sorry, input output waveform, sorry, not characteristics, input output waveform with respect to time. This graph is called as input output waveforms for common emitter amplifier. Okay, fine.
Yeah, sir.
Okay, now next we'll go for the derivation for Rin or Zn, we call it input impedance, or we call it as Zn. So we'll derive this now. Okay, now there is a technique to do that. This I have adopted from Professor Razavi sir's lecture. Professor Razavi. So you can search in Google Bizar Razavi, B Razavi. He's considered to be godfather in microelectronics. So I'm following his footsteps and I'm explaining you this derivation. It's not my own invention. Okay, it should be clear. Okay, or else because this analysis becomes quite complex, you can check it out in your standard books. It's like one lengthy pages of 2 pages, and we'll get the same result. So yeah. So what we do is just listen. How do we calculate input impedance? So we consider the entire circuit inside the box, entire AC equivalent circuit inside the box. Then we apply the test source, external test source to it. Okay, Vx, and we force the current Ix through it. Okay, we apply, we consider the entire circuit inside the box. We apply a test source. Okay, Vx, and Ix is current flowing. So what will be Zn? Zn will be Vx upon Ix. Did you get it? And this is the technique we will apply. Is it fine, everyone? Hello.
Yeah, sir.
Okay. So what is the meaning of putting entire thing in the box? Now see this, what I'm doing. I'll rub it out later. I'll put it in green color. So I'll put the entire small signal circuit inside the box. So let me take it. Okay. I don't know. Huh. This entire thing inside the box, and I'll replace this Vx by V in by Vx, and the current passing will be Ix. Okay. Yes or no? Now, how will I proceed further? Now I want to calculate Vx upon Ix. Okay. So let me draw this up till here. This is what I will do. I'll put entire circuit inside the box. Right now, let me do it additionally over here. Okay. So this was my circuit. So you can also draw it. I'll apply Vx, and this current will be Ix. Now this entire circuit will be in, let's say, blue color. So I have R1 parallel to R2. Then I have R pi over here. Then I have a current source, GMV pi. And here it is open circuit, okay? And this is connected to the ground. So why I'm not drawing the other part of the circuit? The reason is because the impedance offered, the impedance offered by the current source is infinite. Okay, the impedance offered by the current source will be infinite. Okay, so that means whenever the current flows over here, this will be treated as open circuit. All right, so the entire circuit which we were supposed to draw like this will be open circuited from here only. So what is left out now? Can you tell me? This becomes open circuit now. So what is left out? Vx upon Ix is how much? Vx upon Ix is, what do you see? R1 parallel to R2 parallel to R pi resistance, right? Yes or no?
Yeah.
So this becomes my input impedance, Zn. That's it. That is what you need to tell. This is my input impedance of amplifier. Input impedance for amplifier. Okay. Can you tell me what is the input impedance of BJT? It's just R pi. Okay. This is the input impedance of BJT. So what has happened by introducing amplifier? R1 and R2 resistors have reduced the input impedance of the amplifier, which is good or bad for the amplifier, for the voltage amplifier. It is bad for the voltage amplifier. We want input impedance to be higher, and if R1 R2 comes in parallel, then it reduces the input impedance. Okay, everyone has understood the derivation for Zn,
Yeah.
or, or any part unclear?
No, sir.
All right. So now we'll go for output impedance derivation. This is interesting. Output impedance Z out. Okay. Now let me draw the circuit quickly. You don't need to draw. I mean, you can also draw it. I'm drawing the equivalent circuit. Okay. This is GM V pi. This is RO RC. This is going to the ground. This is RL. And here at the output, I'll connect something, right? RC RL, RO. This is going to the ground. This is going to the ground. This is going to the ground. This is R pi. This is plus minus V pi. Alright, this was the circuit, right? Now what we do in output impedance is we again put everything inside the box, entire circuit inside the box, but this time we'll short circuit the input. We'll make V in equal to 0. And now we apply test source at the output instead of input. Okay, so this voltage will be Vx and force the current Ix. So in this now your Vx upon Ix will give you Z out. This Vx upon Ix is Z out, but there is one more condition, that V in should be equal to 0. So let me draw that Vx and Ix now. This is Vx and this is Ix. So I'll put the entire circuit inside the box. So this is the circuit inside the box. Okay, and I'll make V in equal to 0. What is the meaning of making V in equal to 0? Short circuit it, right? Yes or no? Short circuit it. V in is equal to 0. So V in will be equal to 0. If V in is equal to 0, can I say V pi is equal to 0? Yes or no? Because V in and V pi
Yes.
are same. If V pi is equal to 0, can I say Gm into V pi current source will be 0? Hana?
Yes.
So that
Yes,
means
sir.
this current source, if it is 0, it will be open circuit. It will be open circuit, and this will be open circuit and no current will flow over here. So my circuit has reduced to this network now. RO, RC, RL are in parallel, and at the output you apply Vx and Ix. So tell me what is Vx upon Ix looking at the circuit RC RL. So it will be RO.
RO parallel to RC parallel to RL.
Yeah, perfect. Yes, that's the input impedance. So that is Z out. It's very easy this way, right, to derive. This I have learned from Professor Razavi's lectures. It's a very shortcut technique and it's equally valid. So this is the output impedance of BJT amplifier. Okay, in common emitter mode. Got it, everyone?
Yeah, sir.
Okay. Now let me tell you some changes if there are any, this thing. Let's say if RSIG was connected in the circuit, what changes will we have? So if RSIG was connected in the circuit like this, let's say, if RSIG was connected in the circuit, what changes it will make? So now your this will be your, let's say, any voltage V1. Now V in and V1 are not same because they are separated by RSIG. Yes or no? Correct. So this V
Yeah.
out upon V1, here in this case V out upon V1 would have been my AV, that is minus GMRC. Okay. Now if I want to calculate AV total, V out upon V in including RSIG, then it would have been V out upon V1, V1 upon V in. This additional factor I need to calculate. Okay, this V1 upon V in. Now this how will I calculate? Let me draw this over here. V in, this is RSIG. This is if RSIG is present in the circuit. Okay, this is R1 parallel to R2, and here we have R pi also. All right. What is this voltage called as? This voltage is V1. Okay. Now tell me what is V1 in terms of V in. Voltage division rule, na? V1 is this resistance divided by this plus this output resistance. So R1 parallel to R2 parallel to R pi divided by R1 parallel to R2 parallel to R pi plus R6 into V in, right? So instead of writing input V in, it will be V1 upon V in. So this is the additional factor which comes if RSIG is present. So if you remember, if RSIG if substitute 0, this V1 upon V in will become 1, right? If we substitute RSIG equal to 0. Okay, got it? We can alternatively write this as, this is Zn only, right? R1 parallel to R2 parallel to R pi is Zn only. So like this also we can write. Okay, this additional gain we can find, additional factor we need to find, and then multiply with Gm into Rc or Gm into Rc parallel to Ro parallel to Rl. That's how we will find that. All right, everyone. Can we move on now with the numerical part? You have understood
Yes.
how to derive and everything else. Okay, fine. So let's move on to the numerical now. So write down. This is your numerical on. They can ask you either numerical or derivation. Okay. I have already informed you all in the strategy ahead. They can ask you to derive AV, Z in and Z out, or they can ask you to find out AV, Z out, and Z in. So write down. Find the voltage gain AV, uh, Z in, and Z out for the following amplifier. Okay. So please draw the amplifier part. Okay. This is VCC 16 volt. This is RC 2.2K. this is R1, this is R2, RE. Okay, and we have coupling capacitors connected over here. RL is also given to you 10k, and this is V out. This is V in given to you like this. And we have a bypass capacitor also. All right. This is the data given. R1 is 90 kilo ohm. R2 is 10 kilo ohm. And here the given data is beta they have given it as 210 and VA they have given it as 100 volt. This is the BJT parameters and it's NPN transistor. Also your input is applied to the base terminal. This is the base, this is the collector, this is the emitter. Input is applied over here and output is taken from the collector terminal. So that's why this configuration is CE amplifier. Okay. So it doesn't matter even if the values of CC1, CC2 and CE are not given because they are not going to be useful over here right now. Still if you want to write, you can write it as 1 micro and 22 micro farad. It doesn't matter. It is not involved in calculation right now. It will come in handy in module number 3. Okay. Can we start? Have you drawn the diagram?
Yeah, sir.
Okay. So we'll start and do the complete numerical together. So first of all, let me explain you the strategy, what we are going to follow. So our aim is to first do the DC analysis and find ICQ for the transistor. Once you find the value of ICQ, calculate GM, calculate R pi and calculate RO. Once you calculate all these three, do the AC analysis. And in AC analysis, you find AV, Zin and Z out. So if I want to give mark distribution, 2 marks will be for ICQ, 3 marks will be for GM, R pi and RO, and 5 marks will be for AV, Zin and Z out. Got it? So let me start with the solution. Okay, so what do we do the first thing? First thing we do is DC analysis. Alright. In the DC analysis, we'll replace all the capacitors by short circuit or open circuit. Open circuit all capacitors. So the circuit diagram will be like this. Let me expand it now. Yeah, it's a voltage divider bias. This is R1, R2, RC, RE. Now you know what we did to the voltage divider bias. We applied Thevenin's theorem at the base terminal and we get this equivalent circuit. We have done that. I am not explaining it further. So this will be VTH RTH. We have seen last time, right? This is RE, this is RC, this is VCC, and that will be ground. If I want to mark the currents, I can mark it like this. This is IB, IC, and IE. This voltage will be VBE. This voltage will be VCE. Okay. And now if you don't remember the formula for IBQ, it's fine. You draw this diagram and then you say that you apply KVL to the base emitter loop. Okay. Are you okay with the pace or should I slow down or increase my speed?
This is fine, sir.
Okay. So next I'll apply. We write over here. Apply KVL to base emitter loop. So what is my base emitter loop? My base emitter loop is this. Here. This is my base emitter loop. The yellow color portion. So how do we apply KVL? VTH minus IB RTH minus VBE minus IERE is equal to 0. Now what is IE actually? IB plus IC. And what is IC? Beta times IB. Correct? So this will be 1 plus beta times IB. So let's do that. So VTH minus IBQ RTH minus VBE minus 1 plus beta times IB into RE is equal to 0. So from here isolate the terms of IB and put everything else on the other side. So it will be VTH minus VB upon RTH plus 1 plus beta times RE. This we have to do in case you forgot the formula. Forget the formula of this IB. Okay. So please calculate these numbers. Acha, what is VTH formula by the way?
R2 upon R1 plus R2 into VCC.
Yes. So please calculate VTH first, and RTH we need. RTH also we require. It is R1 parallel to R2. So please calculate these two numbers. VTH will be R2 is 10. This is 10. R1 is how much? 90. VCC is how much? 16. So this comes out to be 1.6. Yes or no?
Yes, sir.
And R1 parallel to R2 will be this is 90k parallel to 10k. So result will be less than 10k. In fact, it is 9 kilo ohm. Correct? I'll give you some time. I'll wait. So I substitute over here 1.6. VB I'll assume it to be zero point 0.7. Assume 0.7 divided by 9 kilo ohm plus beta is 210. So it will be 211 into RE value is 680. So calculate the value of IBQ. So I'll give you all some time to calculate this. Do it with your own calculator to gain confidence. Okay. Hello. Anyone got the value of IBQ? IBQ will always write in microamperes. Okay. It will
तो
always.
रहेगा so 5.9 microamperes.
Yes, it's correct.
5.90 microamperes.
Yes, it's correct.
Yeah.
It's 5.9 microamperes. That's the correct value. Now, once we got the value of IBQ, ICQ will be beta times IBQ. So 210 into 5.9. That is how much? 1.239. Yes.
Yes, sir.
Okay. So please note it down. Completed. Okay, fine. Next, let's calculate the small signal parameters. That's the A part. So the B part will be calculate small signal parameters, that is GM, R pi and RO. You remember you have written the formula. So first calculate GM. ICQ upon VT. That is 1.239 into 10 raised to minus 3. What is VT? 26 millivolt. We have to assume it if it is not given. So how much is this? 47.67 milliampere per volt. Got that?
Yes, sir.
R pi value will be beta upon Gm. So beta is 210 divided by 47.67 into 10 raised to minus 3. Calculate R pi, and RO is VA upon ICQ. Early voltage is 100 volt divided by current. So please calculate now R pi. So this is 47.67. Anyone got that? R pi value how much?
4.40 milli ampere value.
No, no,
नहीं नहीं
4.4
अच्छा यार
kilohms. It's a
सॉरी किलो ओम हाँ ये रेजिस्टेंस है ना हाँ सॉरी
resistance.
या सर रेजिस्टेंस है
And
किलो
RO will be around 80.67 kiloohms. 80.68 kiloohms. Did you get that answer correct?
हाँ सर
Okay, got it. Now, let's move on to the third part. So this will fetch you 5 marks out of 10 up till here if you complete. But you need to complete the entire numerical. So now we know the formula for AV, right? It's simple. RSig is not given. So it is what? GM RO parallel to RC parallel to RL, correct? All three are given, right? And if they ask you, you need to draw the small signal AC equivalent circuit. For the time being, I'm not drawing it to save the time. But in the exam, if they tell you to draw it, you have to draw it. Okay? And it's safer side to draw it. Some teachers give marks for drawing this also as 1 mark. So do that also. Now you tell me what is RC parallel to RL. Calculate RC parallel to RL first. How much is that? This is 2.2k parallel to 10k, and then it is parallel to 80.68k. So can you tell me this? How much is this? 2.2 parallel to 10 kilo ohm. How much it is? Anyone? Hello.
so is it 1.8 kilo ohm
Okay. I don't know. I don't have. I know the all
अच्छा
the value together. Exactly. This will be 1.8k, 80.68k parallel to. This result I know. Its value is 1.76. Okay. So this GM will be 47.67 into 10 raised to minus 6 into 1.76 into 10 raised to 3. Did you get 1.76?
Yeah, sir.
So this number will be
हाँ सर
83.8. Calculate the voltage gain. Actually, I should have started with R Z in and Z out first, but it's okay. Always start with Z in and Z out. For voltage gain, it's fine. You can find at the end. So you should get the voltage gain as minus 83.8. Got it? Hello. Anyone got the value similar? 83.8.
Yeah.
Okay. Then actually we should have actually calculated Z out and Z in first, but it's okay. So let me write down the value of what is Z out. Do you remember? How much is the answer? Did you understand why I was saying right first? Is this only correct? And how much is Z in? R1 parallel to R2 parallel to R pi. R1 parallel to R2 we know now already how much it is. 9 kilo ohm. 9 kilo ohm. So 9 kilo ohm parallel to R pi. R pi is 4.4. Yeah. How much is this? This is I think 2.95 kilo ohm. Please check these answers, please. Yeah.
Correct, sir. Correct.
Okay. Yeah. So calculating this much will fetch you full marks. Got it. So yeah. So you have calculated BJT amplifier, common emitter amplifier numerical. I'll wait for 30 seconds and then we'll move on to the next one. Any doubts anywhere you can ask right now because we are into the numerical. So we have gone by this strategy. First we have found out RCQ, then GM R pi RO, then AV Z in Z out. Okay. Everyone ready for the next one? Anyone having any doubt?
Yeah, sir.
Okay, fine. So it's fine. I'll go to the next one. So next one is degenerated. It's the other name actually, common emitter amplifier. It is basically common emitter amplifier with RE unbypassed. मतलब capacitor CE is absent. Okay, with RE unbypassed. So I will not derive it. I'll write down the expressions and I'll show you the derivation how it's been done. So first of all, draw the circuit diagram quickly. Entire circuit diagram is same. Only don't draw CE. Capacitor CE don't draw. That's it. And here for a derivation we have relaxed R out also, RL also. This is CC to VCC. This is going to the ground. CE is not present, okay? Except that everything is present. That's it. This much is given. Capacitor CE is bypassed. So what happens is I'll explain you with relative grade. So basically this gain AV, whenever we have a CE capacitor connected, this gain is very large but is unstable. In your lab also when you did the experiment, you got the value of voltage gain, must have got the value of practical value and calculated value slightly deviated, right? Whereas if you just remove CE, this gain becomes more stable but it reduces its value. Okay, so with this configuration the advantages are the voltage gain has reduced but has become more stable. So what's the formula? We will not derive it, we will see what's the formula. We'll go through the derivation. So write down the formula. It's minus RC upon 1 upon GM plus RE. This is the formula. Now you can easily relate it over here. If we substitute RE equal to 0, what the formula becomes? Minus GMRC, right? Same as previous equation. Yes or no? So this is with no RL connected, no RO, small RO also. This is the formula for that. Okay. Now what is the formula for Z in? Up till here it's same, R1 parallel to R2 parallel to R pi, but here it will be some change will be there. Write down these formulas. 1 plus beta Re. So that's the change. Okay, this 1 plus beta Re into beta into Re, what this indicates that Zn value has increased. That means input impedance of the amplifier has improved. So Zn has increased from normal CE amplifier. And what about Z out? Z out will be same as RO. Okay, so Z out remains same and AV is reduced but more stable. So this is the summary of degenerated common source amplifier. Everyone has written the formulas in the exam. If they ask you, if they don't give you the value of C, that means it's a common emitter amplifier with RE unbypassed. Okay, and these are the formulas. Now remember, in this expression Z out, if small arrow is given, RL is given, all of them will be in parallel. Okay. Any doubts, students?
No, sir.
Okay. Now let me show you the derivation in brief. That was lecture number 11, I guess. Okay, let me show you the. Yeah. No. Let me. BJT amplifier it is. Yeah. Yeah, here it is. Can we start? Please, it will listen to it 5 minutes, and then we will. Are all of you ready? Can you see this actually? It's okay. Visibility is fine. There's already PDF
Yeah, sir.
document. Okay, we'll go through the AC analysis. So this is the AC analysis. Everything remains same, but only thing is emitter terminal is not grounded now. See, emitter terminal is not grounded now. Rest everything is same. All right. So how we'll derive now this thing? Voltage gain formula. You apply KCL at collector terminal. So what do you get? This is V out upon RC. This is GM V pi. So what do you get? GM V pi plus V out upon RC is equal to 0. So V pi will be minus V out upon GMRC. This we call it equation number 1. Okay. So now we'll apply KCL at the emitter node. Emitter node. So what does the KCL at the emitter node says? Okay, this derivation. Yeah, you apply KCL at the emitter node. So KCL at the emitter node is current through RE. What is current through RE? Current through RE will be, let me use this thing, will be this current. Okay, let me use color. Will be this current plus this current. Yes or no? Addition of two currents, right? Hello.
Yes, sir.
Yes, sir.
Okay. So what is this current? This current is V pi upon R pi, and this current is GM V pi. So that's what we have written, current through RE into RE. Okay. So KCL will be current through RE into RE is equal to voltage drop on RE. Okay. This is equal to voltage drop, right? Okay. Now this V pi, we substitute this value from here. V pi is minus V out upon GMRC into 1 upon R pi plus GM into minus V out upon GMRC, right? And that is equal to voltage drop on RE, VRE actually. So we have written VRE is current through IE into RE, and this is IE. All right. So from here we go further. Now we write KVL in the base emitter loop. So what does the KVL in the base emitter loop says? If this is V in, KVL in the base emitter loop means here. So what does the KVL says? V in minus this is V pi minus VRE is equal to 0. Correct? V in minus V pi minus VRE equal to 0. This voltage across RE is VRE. Here. Here, this one. So this is the KVL we apply. That's what we have written. V in is equal to V pi plus voltage drop across RE, which is VRE, which we have calculated. So you plug in the values, rearrange the terms, and then you will finally get this formula. Okay, I'm not going to the detail. This is just a, I'll share this PDFs with you all. I think I already shared with this you all. All right. Now this can be further simplified further. This can be simplified further below. So multiply and divide by beta into GM. So you'll get this. Now here you can assume 1 plus beta upon beta is 1. And that's how you land up into this formula. Minus RC upon 1 upon GM plus RE. Got it? So you refer to the derivation, okay? Fine. Now for input impedance, you put the entire circuit inside the box and you apply the test source at the input, and here you force the current Ix. So Zin will be Vx upon Ix. Over here only one difference is there. This Re is present. Okay. So now what we do is, to simplify the analysis, we have pushed this R1 parallel to R2 on the other side, on the left hand side. See this here, like this. And now we are analyzing this circuit. Okay. So if this current is Ix, what will be this current? This current is base current. This is IB. So what is IE? IE current is 1 plus beta times IB, right? So that's why emitter current is 1 plus beta times Ix, because Ix is the base current. Did you get it? 1 plus beta times Ix. Now here we need to find out the value of input impedance. Okay, whatever the value of input impedance will be, ZIB, that will be in parallel to R1 and R2. So here we write what is V pi. V pi is Ix into R pi. Okay, and your GM V pi will be GM into Ix into R pi, and your GM into R pi is nothing but beta, and beta Ix is nothing but IC. Okay, beta IB is nothing but IC. So current flowing through RE will be IE, which is 1 plus beta Ix. Are you following? Hello. uh, can someone please reply?
Yes, sir.
Okay, I'm just going through a little fast. You can go through these documents later. Okay, now we apply KVL to the base emitter loop. So KVL again will say that here we apply the KVL. Here again we'll say that Vx is equal to V pi plus VRE. Okay, so here we write V pi is equal to, Vx is equal to V pi plus VRE. What is Vx? Ix into R pi, and VRE is 1 plus beta Ix into R pi. Okay. Now from here we take the Ix common and we'll get inside the bracket this. Now this is Vx upon Ix, R pi plus 1 plus beta Re. So this is ZIB. ZIB, right? But our actual resistance will be R1 parallel to R2 also. So that's why total input impedance will be R1 parallel to R pi parallel to ZIB, where ZIB is R pi plus 1 plus beta times Re. So here we get high value of input impedance. Got it? Now for output impedance, actually we make V in equal to 0. When we make V in equal to 0, your you know V pi, we need to calculate it. So this is what we get. We redraw the circuit with V in equal to 0, because now Re is present, right? So we cannot directly write eliminate this things as it is. So what we do is, for simplicity, we push RC on the left hand side, on the right hand side of this Vx source, like this. And now we calculate ZOB from this circuit. Okay. So from here, what is VRE? VRE is actually VRE, this voltage. VRE is actually opposite of V pi, minus V pi, right? And we apply KCL at node E. So what does the KCL at node C says? This current, this is V pi upon R pi. This current, these are two incoming currents, and that is equal to outgoing current. And outgoing current is nothing but uh, VRE upon RE. Okay, so V pi upon R pi plus GM V pi is equal to VRE upon RE. Now VRE is minus V pi and upon R pi, right? So here if you check, you will get V pi equal to 0. Now if V pi is equal to 0, GM V pi will be equal to 0. That means your current source will be open circuit now. So ZOV will be infinite. That means output impedance is just RC. We have to prove it. Huh? We cannot write directly that current source is infinite in this case. Because in earlier case, emitter was grounded. In this case, emitter resistance is present. Are you getting it? So will you refer these derivations, students? Okay. Please refer these derivations. This will be given in BJT amplifier PDF. I think I have uploaded that in the last time I have given you all, right? Is this fine to you, everyone? Hello?
Yes, sir.
Yes, sir.
Okay, fine. Now we will discuss. There are two amplifiers left now. Common base amplifier and common collector amplifier. So tell you all. I'll do it parallelly, and then I'll write the results, and then we'll go to the derivations. Okay. So draw the common base amplifier. Okay. Let me reconnect my writing pad. Okay. Okay. I guess it's letting bit loaded. Actually, we have written too many things in a PDF, right? So that's why it's taking some time. Yeah. Now it's fine. Draw the common base amplifier circuit diagram at least. Okay. So again a voltage divider bias will come. This is R1, R2, RC, RE. Okay. Now in this case we apply the input to the emitter terminal. So this is the emitter terminal and we apply the input over here. And we take the output at the collector terminal like this. This is V out. Okay. This is CC2. This is CC1 and this is called as blocking capacitor CB, same as your your bypass capacitor, but this is blocking capacitor. This is the CB configuration. Your input is applied to the emitter. Input is applied to the emitter and output is taken from collector. Okay. Have you drawn the diagram or can I proceed ahead? So whenever input is applied to the emitter terminal and output is taken from the collector terminal, that configuration is called as common base amplifier. Alright, and its voltage gain formula will be as follows. Exactly same as its formula is exactly same as common emitter configuration, but with a positive sign, plus sign. Okay, if RO and RL are present, then its formula will be RO parallel to RC parallel to RL if they are given. Okay, so if RL and RO are present, got it? Same formula but plus sign. So that means input and output are in phase. For common base amplifier, the input output waveforms are like this. If this is time and if this is input, okay, my output will be like this. I mean, okay, got it? You have understood, right? And your input impedance will be, I hope I'm audible now. My input impedance will be very low. That's the feature of this amplifier. Input impedance is very low. It's not good for voltage amplifier, but for current amplifier it's very good. And Z out. Z out will be again same as your normal amplifier, CE amplifier. So Z out derivation will be same. So this is V out of T. This is V in of T. They are in phase with each other. Can someone reply if I'm audible because I've not heard your voice since. Hello.
Yes,
Yes,
sir.
sir.
Okay, okay, y'all are quiet. Okay, fine. So, in many terms, CB amplifier and CE amplifier expressions are almost same. Only Zn expression is slightly different. 1 upon Gm parallel to Re, and R Z out is equal to Rc. And AV is same expression, but only positive sign is there. And this is my input-output waveform for common base amplifier. Okay. Now we'll see in comparison. Uh, You'll have written the formulas. Hello.
Yes, sir.
Okay. Now in comparison, we draw common collector amplifier. Common collector amplifier also is similar in quite terms. Only thing is RC is not present over here. Capacitor RC is not there. So don't draw RC. Okay. So this is my configuration for common collector. R1. Let me draw plus VCC. So this is my collector terminal. Input is applied to the base terminal over here. V in. This is R2 RE, and output is taken from the emitter terminal. That's the difference. This is V out. So input is applied. This is CC1, CC2. Input is applied to the base, and output is taken at the collector or emitter. Sorry, and collector is directly connected to VCC. So this configuration is common collector configuration. Now here also assuming that early voltage is infinite, early and so that RO is infinite, let's write down the formulas for AV. Let's write down the formula for AV, gain AV. So AV will be, please write down the formula, RE upon 1 upon GM plus RE. If a small RO is present, then what will be the formula? This, parallel to RO. Okay. If RL is present, then again RO parallel to RL. So this is the formula for AV. Okay. If RO is infinite, just remove it. That's it. So if RO is present, this is RO present. And if RO is not present, then the formula will be this. Okay. So this is RO not present. So what is the feature of this formula? The feature is that your gain AV is less than almost equal to unity. So basically any amplifier whose gain is unity, we should not call it as an amplifier. So this is has application as voltage buffer, or it is also used as an isolator. Okay, it's not used as an amplifier basically, but we still call it amplifier. We call it emitter follower. The other name for circuit is emitter follower. Got it? And what is the input impedance given by over here? Input impedance is R1 parallel to R2 parallel to R pi plus 1 plus beta times Re. This is the input impedance. Output impedance will be 1 upon Gm parallel to Re. Yeah, these are the formulas. And if Ro is present, wherever there is Re, replace it by Re parallel to Ro. Okay. So this is the summary for common collector configuration. Hello, did you get it?
Yes, sir.
Okay. Now let's briefly see those derivations. Um, Lecture number 12. Okay, this is common base amplifier. I'll only show you the this thing equivalent circuit. I'll not explain it. You try it out on your own. Yeah, this is common base amplifier basically. Yeah. So this is the common base amplifier. You first draw the equivalent circuit and now replace the BJT by its small signal model. So this is how your circuit will look like. Now for this circuit, we need to derive the formula for V out upon V in. Now I leave that exercise to y'all. Y'all can refer this PDF. I've already said, I guess, right? And yeah, you can see it's plus GMRC coming up. Similarly, for Zn derivation, you can, I leave that exercise to you again. You find it out and it will come out to be 1 upon Gm parallel to Re. Okay, just to save time, because I've explained one in detail. So other things are similar. Only thing is you need to apply KCL KVL to get the equation. You can try it out on your own. Okay, then yeah, its application is it's used to drive a low impedance source such as an antenna has a low impedance, and input impedance of CB amplifier is also low, so there will be impedance matching and then signal will pass as it is without any loss. So it's used in case if the input source is having low impedance. Now the output impedance, again put everything inside the box, V in equal to 0, apply test source, same technique. So here you get R out as or Z out as RC. Got it? So please refer these derivations for common base amplifier. Now I will show you the numerical. So I'll asking you, do you need to solve a numerical? Because its procedure is same, only calculation formulas are different. So is it okay if I just describe it, or shall we solve it? I leave up to you. Hello. Should I explain it or shall we solve it together? I am ready to do anything. It's exactly same.
एक्सप्लेन ही कर दो सर, एक्सप्लेन ही कर दो, इट्स जस्ट सब्स्टिट्यूट करना है ना वैल्यूज
Yes,
फॉर्मूलाज में.
yes, exactly. We have solved
हाँ
one
वही
and
है,
it's similar.
एक्सप्लेन ही कर दो. या सर.
So
हाँ.
now again a strategy will be to find out ICQ, then find out GM into R pi, GM and R pi, because RO will be infinite because VA is infinite. Then calculate AV, RN and R out, or you can call it Z in Z out. So you first draw DC analysis, convert Thevenin's equivalent at the base terminal, so you get this circuit. From there you calculate VTH and RTH. Okay. Then IBQ formula, please remember for voltage divider bias. You'll get IBQ in microamperes, multiply it with beta to calculate ICQ. Then calculate the small signal parameters GM and RPi. I've seen students forgetting the formula for GM and RPi. So please remember the formulas of GM, RPi, RO. Okay, don't forget that in the exam. If you forget that, everything else will be wrong. So GM will always keep it in milliampere per volt and RPi will be in ohms. Then draw the small signal equivalent circuit. From here calculate AV is GM into RC. You'll get the value positive number. Then calculate Rn is 1 upon GM parallel to Re. You'll get the value very low as I've told you. And R out will be just equal to RC. R out or Z out, we call it interchangeably. Okay. So this is how you solve a numerical on common base amplifier. Alright. I'm just I'm just describing it, that's it. And let me show you now for common collector. Okay. Okay, for common collector we have okay, R out derivations I have shown in the markings. Yeah, this is common collector configuration. Input applied to the base, output is sensed at the emitter. So here you draw the small signal equivalent circuit, and here you have to calculate V out upon V in. I leave the derivation part up to you. Okay, you can refer the derivation. If you have any doubt, you can email it to me. Okay, so here you go through all the steps, apply KCL KVL, and finally you will get this formula. AV is R in RE upon 1 upon GM plus RE. Alright, and it is called as emitter follower circuit. Then for input impedance, put everything inside the box and calculate the input impedance. Apply a test source at the input terminal, force a current Ix. So input impedance will be Vx upon Ix. So here we can calculate Vx upon Ix as this: R1 parallel to R2 parallel to R pi plus 1 plus beta times Re. This derivation is same as your degenerated common emitter amplifier. So this derivation will be same. Result is also same. Now your output impedance formula will be same as input impedance of common base amplifier. You can check out the result. See, this is the same formula for input impedance for common base, which is output impedance of common collector. Now one feature which I want to tell you is that even though the gain of common collector configuration is unity, its input impedance is very high and its output impedance is very low, which makes it a perfect candidate for use as a buffer. Okay, so application wise it's used as a buffer. Now let me show you the numerical. In the numerical only I'll tell you one warning, that RC is not present in the circuit. Okay, and here they have given the value of R sig as 500 ohm. So let's see how do we tackle such numerical. Again the strategy is same. First calculate ICQ, then calculate R pi GM and RO, then calculate AV, RIN and R out, or Z in and Z out. Now entire thing, don't panic, do as it is. Okay, so base emitter loop will not change. Now formula will remain the same. Let collector be connected to VCC. Calculate VTH, RTH. I've seen students making mistake in this also. They forget to write VCC and the answer comes wrong. They only write the fraction. So VTH formula is R2 parallel to R2 divided by R1 plus R2 into VCC. Calculate RTH, then the IV formula will remain same. It will come in microampere. Multiply it with beta, you will get ICQ. Then don't forget the formula for GM, R pi and RO. You will get these values respectively after substituting. Then draw the small signal equivalent circuit. Okay, please draw it. Now as I've told you earlier, if RSig is present, AV formula split up into two parts. So whatever formula we have derived, that is V out upon V in, that is V out upon V1, what we have said before, right? And V in upon Vs will be determined by voltage division rule. So this is the formula for AV if RO is present. So first calculate that. Before that we can calculate Rn or Zn. So Rn will be this formula. So calculate very carefully. Then R out will be this formula, 1 upon Gm parallel to Re. If RO is present, that will be in parallel. You got the value of R in and R out. Then calculate AVT. So we have calculated V out upon V in. That will be over here, 0.9835. Then calculate V in upon Vs by voltage division rule. You see Z in upon Z in plus R sig. So that came out to be 0.978. The multiplication of 2 will give you the answer. Now here what people do is they leave this out. They leave the answer till here. So this is incorrect. You have to calculate one more part. Okay, got it? So this is common collector configuration. And then there is a, I think, comparison PDF is there. I don't know. Any comparison is given. Let me check it out. Yeah, in BJT amplifier it is given, I guess. Let me show it to you, please. The comparison of all three amplifiers. Yeah, this is it. If they ask you in the exam, compare common emitter, common base and common collector amplifier, then these are the three circuits. You should compare, draw the three circuits. Then you say that where is the input applied, where is the output, sensed at, output taken from. You can write this in comparison point. Then write down the voltage gain formula, even simplified formula. Then write down the input impedance and also write whether it is high, low or medium or very high. So output impedance, phase of the signal, whether it's out of phase, in phase, or again out of phase, and applications. So common emitter is normally used as an inverting amplifier because its gain is negative. Common base is used as a non-inverting amplifier. It's also used as a circuit to drive a low impedance source. Okay, and common collector, it's actually not an amplifier, it's a buffer actually. It's used to drive a low impedance load. Okay, whenever you build a, let's say, a voice amplifier circuit, output side is always a common collector because it is used to drive a speaker. Do you know speaker resistance is around in few ohms, around 10 ohms or 12 ohms or even 7 ohms for that matter. All right. So yeah, with this we have come to the end of I think this one. Basic BJT configuration, small signal hybrid pi model of BJT, small signal mid frequency, and don't worry about this term mid frequency. This we will cover when we reach frequency response of single stage amplifier. That will be covered in your class. Okay, so we have done the detailed derivation of common emitter, and we have solved a numerical also. But we have just glanced through the derivations and the formulas and the numerical for CB and CC. All right. So yeah, from my side that will be it. If you have any doubt, you can ask me right now, or else I'll call it off for today.
Sir, what is the pattern paper?
Sir,
Okay, okay, fine. There is no such regular pattern. I mean, it's similar to as you have given in your earlier semester. Like it's an, it's like questions will be asked out of 10 marks, and one option will be there. So yeah.